So there are 5 problems on the test. It took me 25 minutes, which means that it's a reasonably long test. So you better be ready. I'll tell you this on Wednesday, that you can actually start as early as 5 after 9. So that'll give you an hour and 25 minutes. Okay, so let's just tell you the general basic kinds of problems. There's going to be a projectile motion problem. It's going to be fairly straightforward, because if you had to do too much thinking, deep thinking, you wouldn't be able to get it done in time. So I'm going to reference a video that you have in your memory stick that you can watch relative to that. And I have figured out the timing for each problem. So this one took me 4 minutes to do. So if you think about 4 out of 25, it's not quite it's not the longest problem for sure. Let me just say 2 things about this, though. There's 2 possibilities. Let's say we have a projectile that's launched off a cliff, and it goes at some angle, so that it goes up like this, and it comes down. Now, there's 2 cases that can happen. One is it can come down and be constrained by the ground here. And in that case, let's say the height of the cliff is 50 meters. The delta y would be -50. So we're going to define our coordinate system so that x is from left to right and y is positive. So the delta y is a -50 value. And so what you would know in this case is you would know delta y, you know a sub y, which is -9.8 meters per second squared, and you could calculate the 0y. So that gives you 3 out of the 5. And so you can figure out the time and the velocity. Usually it's easier to calculate the velocity, the final velocity v sub y, even if we don't need it, because then we can use that velocity to calculate the time instead of having to solve a quadratic equation. So the second option is if you have some vertical wall, let's say I had a vertical wall like this, what's going to constrain this is the x direction. So for this case, you'd know delta x would be positive. So knowing delta x, you could use that, delta x is v0x times t, and you can find that by the known initial velocity and breaking it up into the components. And so you could solve for t as delta x over t. And this distance would have to be given so you know what you're going to run into. And I see I've got delta x divided by v0, v0x. So that would give you the time. And then you could use that time in the y direction equations to figure out how high you are when you hit the wall. So those are the 2 options. And we did an example in class that you did for homework, and I'm going to show you the video here in a second when I get around to that. So one is projectile motion. There's one which we'll call an equilibrium problem. And again, we did that. We also did an example in class. This is where we had forces supporting 2 cables supporting a weight. And the example we gave you was that I gave you the weight or the mass of this object here that's hanging down, and you use that to find the weight. So you knew the mass multiplied by 9.8 meters per second squared. You got the weight, and that weight equals this force, which I think we called F1. So we knew this. Now, in the interest of making it so that you can solve this more easily, I'm going to give you one of the other tensions. So I'm going to give you like F2 here. Let's say it's some value, 300 newtons. And you're going to be able to use this force diagram to work your way through. So we'll have F2y and F2x, and we'll have, let's call this F3. You'll have F3x and F3y. And in this case, I'm actually going to ask you to calculate the mass. So it's similar to the problem we did in class, but you're going to kind of go back. You're going to go work your way through the problem. And I don't want to tell you how to do it, but you can think about it. You're going to be given these angles. So that'll be some value. I'm going to make up a number, 25 degrees. This one's maybe 60 degrees, something like that. So knowing this, you should be able to work your way around just using the right triangle geometry of these vector triangles to back out what F1 is. And once you know F1, you know that it has to be due to the weight. And once you know the weight, you can calculate the mass. So that's kind of the way it works. And this way, you don't have to solve any, you don't have to do any substitution or elimination. You just deal with you still have to have some of the forces in the x direction are 0, so this minus that has to be 0, and this plus that has to equal that. Okay, so that's all I'm going to tell you about that one. Probably more than I should have in the first place. And then there are going to be 3 problems. Well, they're not exactly in this order, but the remaining 3 problems are going to be motion problems. So we did a lot of those in class. And there's going to be one which is just an object by itself. Actually, there's going to be 2, just an object by itself. So what we have to do there, we're just going to take that object, we're going to draw a free body diagram, we're going to sum the forces in the x and y direction, and we are going to, one is going to be, so of these 2, one is going to be horizontal, so we really don't have to worry about angles as far as inclined planes, and the second one is going to be an inclined plane. And then the last one is going to be 1, which is an inclined plane, but it's going to have a weight hanging inclined. So they're going to be things that are connected together, inclined plane and 2 masses. So you can go back and look, we had the case where we had a mass hanging here, and we went over the pulley, and then we had another mass hanging down like that. And so you do the free body diagram of each one of these separately. The thing that connects them is the tension in these 2 cables is the same value. And also the accelerations are related. The values are the same. They may, depending upon how you define your coordinate system, they may be the same sign or different signs. You have to decide. Okay. So let's go to the so here's the memory stick, and you have physics chapter 3. So you can see projectile motion example. So you need to look that over, make sure you understand it completely, and that you can do it reasonably quickly. So that's the projectile motion problem example. Now in chapter 4, we've got all these examples, and most of them we went over in class. We have horizontal table with hanging weight and friction. We've got horizontal table with no friction. So this is kind of the ones where they're connected to each other, this is the simplest one. And then we go to this one, which is with friction. Then we go to inclined plane, hanging weight without friction. and then we go to this one. So that's the order, kind of this one. If you want to watch that one, then watch that one, then watch that one, then watch that one. And you'll see all the things that get built up as far as the results. When we don't have friction, we don't have to worry about the y direction parts where there's an inclined plane, because that doesn't really help us anything. But when we have friction, we need to relate the normal force to the friction force through the definition of coefficient of friction. So there's those ones you definitely want to watch. Those will give you some examples of what you need to know. This is what is equilibrium, which is, I think this includes information about how you do the equilibrium problem. And this simple kinetic friction example is an object by itself, and it's slowing down. So that's, and also if you look at introduction to inclined planes, that's also an object just by itself. It could be sliding down, it could be sliding down to stop, it could be starting with a stop and sliding down, depending upon what's going on. And with all of these chapter 4 problems, they're basically using Newton's second law to calculate the acceleration. And I have it where you have to then use that acceleration with the equations from chapter 2, the 4 kinematic equations to calculate things like how far does it slide, how much time does it take. So you might have something sliding to stop. How long does it take to stop? Remember, stop is 0 velocities. You might start from a rest, like if you have an inclined plane, you let go of it and it slides down, and your initial velocity there is 0, and your final velocity depends on how far it slides down the plane. So make sure you know how to incorporate the calculated acceleration with using that then in the kinematic equations. You'll also see there's some additional examples. So if you look through these and you want some additional help or additional examples of applying Newton's second law, you can watch these videos as well. So that's pretty much it. You really don't, there's not a whole lot that you, the actual equations you need to know. So I'm going to go ahead and just write those down just to show you that it's not very many. From chapter 2, we have that the displacement is the average of the initial and final velocities times the time. We have that v is equal to v0 plus a times t. We have that delta x is equal to v0 t plus 1/2 a t squared, and this one, we tend to use this a lot, and this should look familiar. We're doing energy right now, so this is pretty much conservation of conservation of energy. Okay, so those are the 4 kinematic equations. We also have, if we're in projectile motion, we have that the initial velocity in the x direction is the velocity, initial velocity times the cosine of theta, and the y velocity is equal to v0 times the sine of theta, where theta is the angle between the velocity vector and the horizontal. So those are our velocities. So when we get to projectile motion, we break it up into these 2 components, and there's also a y version of this equation. I think that's pretty much it. Projectile motion means that a sub y is equal to negative 9.8 meters per second squared, unless otherwise, we're on another planet. And we usually define our coordinate system so that y is up for projectile motion problems. When it comes to Newton's laws, we have for equilibrium that the sum of the forces equals 0 in both the x and the y direction. So this is equilibrium. meaning there is no motion. And we can also, take just like we did with velocities, we can break up the force vector into a y component and an x component. And if this is the angle between the horizontals, then you know that f sub x is equal to f times the magnitude of f times the cosine of theta. And the y component of the force is the magnitude of the force times the sine of theta. You just have to remember also, if you have a force that's pulling in this direction, then you've got a negative x component and a positive y component. If you pull it in this direction, then you're going to have a negative x component and a negative y component. So you have to reflect those in your calculations. If you just use the angle between the horizontal and the vector. If you did it all the way from here, then you wouldn't have to worry about signs. It would automatically work its way out. So it depends on how you like to do it. I like to do it this way because you're dealing with just right triangles, and then you have to give a little thought to the sign. So that's equilibrium. And then when you get to motion, we're either dealing in this case with things moving horizontally or things moving on a plane. We always define, for a horizontal movement, we would define our coordinate system like this. And for a plane, we would define it at the angle of the plane. And so x is parallel to the plane and y is perpendicular to the plane. So in this case, because we do have motion in the x direction, it's going to be equal to mass times acceleration in the x direction. And so it's not equal to 0 like we have for equilibrium. It's equal to the mass times the acceleration, and then you have to put your forces over here. So it's not, so you have to write these out, and you have to reflect the direction based upon what you see in the problem and how you define your coordinate system. Now, in the y direction, for horizontal movement or for on a plane, the y direction, the sum of the forces equals 0. So the force is equal to 0, so then you list your forces. Typically, you have a normal force and you have a weight of some kind, W sub y. If you don't have any friction forces, this equation really doesn't do you any good. So it only comes into play when you have friction force. And the relationship you use to relate these two when you do have friction force is the definition of the coefficient of friction. So you can see if I can find W sub y, then I know what F, the normal force, is. If I know what the normal force is and the coefficient of friction, I can calculate the friction force, which ends up being part of that. Now, if you have something that's moving vertically, then that's kind of the other possibility. In that case, you have the weight pulling down and you have the tension in the cable pulling up. We don't worry about the x direction in here. Again, you can either define y going up or y going down. It all depends upon how you want to do it. If the if the y is going up and this thing's falling, then the acceleration should be negative. The value you should get is a negative value. If you defined y going down as positive, then the acceleration would be positive because it would be in the same direction as the y. So, you might just want to choose one way and stick with it. Since we do positive y and in all these other cases, you might want to just make it positive y so you don't have to think about it. And then know that if this is moving upward, it's positive acceleration. It's moving downward, it's negative acceleration. Or at least in terms of acceleration, if it's falling or being pulled up. So in that case, we don't worry about the x direction. We just have the sum of the forces in the y direction are equal to the mass times the acceleration in the y direction for this part. And so typically when you have more than one object that are connected by a cable, the thing that connects them is the tension. There's two things that connect them. So connecting two objects that are multi-part is the tension in the rope that connects the two. And is the acceleration. And that depends upon how whether it's equal to or whether it's equal to the negative of. You can watch the review, you can watch the examples and hopefully understand that. And typically what we do is these are the two unknowns that we have when we fill in all the information that we have from these equations. Typically this one, and we have this one. They both contain accelerations. You have to you have to use some relationship between these two, and they should be the same magnitude. Maybe, like I said, depending upon how you define the coordinate system, maybe the same or negative. Typically what we do is we solve for tension in one equation and substitute it into the second equation. So the only unknown is acceleration. Then you solve your equation for acceleration, plug in the numbers, solve for acceleration, and then once you know that, you can go back and plug it into the equation that you solve for tension. And I'm going to ask you for both of those. So make sure you feel comfortable in not only calculating acceleration, but going back and calculating the tension in the cable. So if you have any questions after you've watched this and also reviewed the videos I have suggested, just come and see me.